Hello everybody, in this exercise we are going to complete a unfinished layout of a wind farm and then obtain the aggregated parameters value for the wind farms and also compare the output of the aggregated with the detailed model of the wind power plant. We can see the studied system in the figure 1 of the exercise document. Let's open the provided Simulink model for this exercise and check the control mode of the wind power plant to make sure that the correct control mode is selected. As always, we can check the model setting and also model properties to be sure about the solver type and also these callbacks function which are inserted in the preload function and initial functions. That is important to note that this preload function, whatever we put there, it will be run once at the beginning when we open the Simulink file. And later, if we make some change in the script, for example, in the parameters file in this case, they will not be evaluated if it is only inserted in the preload function of the callbacks. So the first task in this exercise is to complete the wind farm layout. If we compare the figure 1 and figure 2 with the wind power plant model in the Simulink file, we can see that wind turbine 4 and wind turbine 7 are missing in the Simulink file. So we need to add them. By looking into the provided figures, we can identify the location of wind turbine 4 and wind turbine 7. Then let's add them. We can use one of the wind turbine motors and also the cables. Make a copy of that for wind turbine 4 and similarly for wind turbine 7. And also use the correct names for the wind turbines. As we mentioned before, the naming doesn't change the performance of the model, so it doesn't matter. It's just for our own understanding. You might have noticed that there are two names here for the wind turbines. One is the name which is given to the block from MATLAB. The other one is the one that we introduce when creating the mask of the wind turbine model. If you want to change the other one also, you can do it by first making that visible and modify it. So here you can see that we will face some errors. That is one of the difference. The namings that we are giving to the wind turbines can be repetitive, but the namings that the MATLAB is giving to each block cannot be same if they are on the same window. So let's hide the names and go to the exercise document. For the running the parameters file, we did it by initial function of the callbacks, um, and also for the building the wind power plant layout, we already added the wind turbines, but we haven't inserted the uh, cable parameters, which are the type and lengths of the cables. So let's do that and insert the type and length of the cable. You can modify the name of the cables as well if you like, but let's look at the exercise document. So next step is to run the model and let's make it 10 times faster to save time in the tutorial. Now if you open active and reactive power of wind turbine 10, we can see the signals. The range of reactive power is less than the previous one because we have multiplied the reference of reactive power by 0.5. In this exercise, we don't need to go to the limit of the wind turbines for the reactive power and even for the active power. because the main focus is not to see if the wind power plant is matching the grid code requirements. The main purpose is to compare the detailed and aggregated model. So that is why we multiplied by 0.5 for stability reasons, because when we go to the limit, it's a bit difficult to stabilize the system. Also, like previous module, the data are logged to the workspace from Simulink, and you can see the namings in the scope. In the workspace, the signals are available. And now, based on this logged data, we can plot P versus Q. After running, we get the PQ chart for wind turbine reference and wind turbine 10, which we are getting the signals from, and also wind power plant and onshore point of connection. The Q range here, you can see that is reduced respect to the previous module, and that is again because reference for reactive power. Also, another point is that the active power of wind turbine is a little bit less than a reference value. If you follow the signals, we can see that the PQ measurement is measured at the filter bus of the wind turbine, while Pref is given to the DC link model of the wind turbine. So we can say that this difference is due to the resistance of the filter of wind turbine, which is located between the measurement point and where the Pref is going to, which is on the DC link of the model. Similar discussion can be done for the active power of wind power plant and also the active power at onshore point of connection. In next part of the exercise, we are going to obtain the aggregation parameter values using the provided scripts. You can take a look at the script to see how it is working. At the beginning, the data are given, for example, length of the cable, type of the cable, and the RLC value for each cable segments, and the number of wind turbines which are connected to each cable segment. And finally, the aggregated values are calculated based on the aggregation equations. We saw that wind turbine 4 and 7 were missing, which means the associated cables were also missing in the model. So let's add the parameter values for these two cables in the script. We can look at figure 2 to understand the type of the cables. So here it says 1000 is type 2, and in this figure we can see both of them are type 2. So type 2 is for cable 4 and for the cable which is coming from wind turbine 7. We don't need to do anything in this part of the code for RLC values of the cable segments because it will take the RLC values for added cables from the parameters files. We just gave the type and lengths, the rest will be automatic. Finally, we should add the number of the wind turbines which is connected to each cable segment. To cable 4, we can see 2 wind turbines are connected, or the power of 2 wind turbines is flowing through this cable segment. And for cables number 7, it will be only 1 wind turbine. Now the aggregation code is finalized, so we can run it to get the aggregated values for R, L, and C, which can be observed on the command window. In the next step, let's convert the aggregated parameter values to per unit, so we can have a sense of these values respect to the values of other components in the wind farm. For doing that, we use the rated power of the wind power plant as the base power, and also the voltage of the wind power plant collector system as the base voltage. If you are wondering how do we know that these aggregation parameter values are the physical values and not the per unit values, you can go to the parameter file and look at the cable data. There you can see the parameters value are given in ohm, Henry, or farad, which are the physical values. So the aggregation parameters which are obtained based on these values will be also physical values. So S base, we define it as the nominal power of wind power plant. For the voltage, the rated voltage of wind farm. Then we can obtain the base value for impedance based on the voltage and power. The base value for inductor will be Z base divided by omega base. So we need also omega base, which is 2 pi F nominal. Similarly, for base value for capacitance, it will be 1 divided by ZB times omega B. Then we can divide the aggregated values by the base values to convert them to per unit, to obtain the per unit values of these parameters. Now here we can see the per unit values. We can compare it with the transformer parameter values, which are in per unit also. So if we compare the numbers, we can see that the aggregated values are very small because the collector system or the wind power plant here is very small. Apart from the simplicity and other things which you know about the advantages of aggregating, when we have a big wind farm, it's a bit difficult to understand the equivalent value of a collector system. But when we do the aggregation, it will be only one segment and it can be compared with other parameter values in the system easily. We said that we are using rated power and voltage of wind farm as a base value, and we could see it from this measurement bus. In next part, we are going to build the aggregated wind power plant model. Let's save the model and add the aggregated at the end of the file name, so we know that it's the aggregated model. The new name of the model should appear at the top of your Simulink model. If you look at that at the very top of the window. Then for building the aggregated model, we need only one wind turbine. So let's remove all cables and wind turbines except for one. We keep wind turbine number 10 because it has these measurement signals that we will use for plotting purposes. When doing this connection and the modification, the most common mistake that might happen is the phase connection. So just make sure that all the phases are connected to the same phase in the three-phase system. Let's change the background color of this measurement block to yellow, so it's easier to see the label of the ports. If we look, we can see that all the phases are connected accordingly. Now we need to modify the parameter values of this aggregated model. For the cable, we set the length to 1 and insert the aggregated value of RLC. Also for wind turbine, we need to change the parameter values specifically for power. Now the power, this wind turbine is actually equivalent to the whole wind power plant, which consists of 10 wind turbines. So we multiply the rated power by 10. We need to scale DC capacitance. Other values are on the wind turbine model are either in per unit or hasn't changed. For example, the voltages, and we don't need to be worried about that. The other thing that we need to do before running is changing names of the logged signals and add the aggregated at the end of the names. We do that to be sure that we are not overwriting the previous signals that we got from the detailed model, because we want to plot the result of detailed and aggregated together. So we want to have both of them available in the workspace. Actually, we need to only change the naming for the signals that we are going to plot, but just to make it straightforward, let's change the namings for all of the signals. If we look at the workspace, we can see the logged signal from previous run are available in the workspace. A very important point here is that we need to keep these logged signals from the detail simulation model in the workspace, because we want to because we need them for plotting purposes. We can either remove this clear all from the parameter file, or we can remove the callbacks functions in the Simulink model. You easily will notice that the model runs very fast with the aggregated model, and that is one of the advantage of aggregation, which makes it very simple. We can see new signals are logged into the workspace, and for each variable we have two signals. So having these signals, we can open the comparison plot. Here you see that only reactive power at the wind power plant point of connection is plotted. So that is why I mentioned before that we only need to rename these signals. The rest we do not use anyway. And by looking into the plots, we can see that the two responses are matching. Even if we zoom in, it will be obvious that the difference is very small, which means aggregation is accurate in resembling the response of the detailed model. This is very useful when we are going to analyze and model very large wind power plants. Before finishing this tutorial, I would like to show you another method for changing the name of the logged data to the workspace. So you can play with that also to see how does it work. For that, we need to go to model setting, and then this part in data import export. There is an option of single simulation output. If we check it, it will collect all of the log data to one variable and save it in the workspace. It will be good that you try to use it. For that, you need to change a bit the plotting script. I recommend that you try to do that. It gives you a good understanding of this feature of MATLAB Simulink. And here we finish the tutorial.